Good day, viewers. Good day, viewers. This is Ademola Johnson, your chemistry tutor and your biology tutor. I have come again. Please do share this video, like it, and subscribe. So don't forget our physical lectures in PostUME, in JAM, in WAEC, in NECO, nursing entrance have started in Stereometric Academy, and the time is 5 to 7:30 p.m. because we have constant solar light. And the venue is Stereometric Academy, Sapley Road, kilometer 8 at Total Street, Total Junction. So we are continuing our work from isomerism. Don't forget, we want to start with stereometric isomerism, which is also known as stereoisomerism. 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 So we have said that this is the occurrence of two or more than two organic compounds with the same molecular formula and the same structural formula, but different spatial configuration. Different spatial configuration of atoms in their molecules. So unlike structural isomerism that I discussed earlier, that one we say occurrence of two or more organic compounds with the same molecular formula but different structural formula. But here now, they have the same molecular formula, they have the same structural formula, but they now have different spatial configuration. So now, let's look at, there are three types of stereoisomerism. These are, we have number one, we have what we call enantiomerism, which is known as optical isomerism. Then number two is called diastereoisomerism. And lastly, we have geometric isomerism. So we are going to discuss these ones in 3 different videos. Okay, let's talk about the first one, enantiomerism. Enantiomerism. Now, when we're talking about this, say this is the occurrence of two organic compounds with the same molecular and structural formula, but different mirror images, or with different mirror images which are not superimposable on each other. What do I mean by superimposability? If you look at a mirror, your right hand, your image that is shown to you, the same hand, this hand, if it were to be not a mirror image, somebody standing in your front. The right hand of that person is supposed to, when it's facing you, it's supposed, your right, if you are stretching right hand, it's supposed to stretch the hand from this side, but it's stretching the same hand. So that means the mirror images are not superimposable. If we take a mirror to look at a wall clock, 12, we turn something like this, something like this, something like 2, instead of 6 like this, you now be having something like this. So this one is the mirror image, and the two of them are, I think they are superimposable, as this one should also be then this one are superimposable, this one are not superimposable. So that is that. Now, the isomers of enantiomerism are called enantiomers. Enantiomers. Let's look at an example of that. Enantiomers. Okay? Now, there are 2 types of enantiomers. Now, what are they? These are, number 1, we have dextro-rotatory compound, and then we have livo-rotatory compound. And take the first one, dextro-rotatory compound. This is a member. This is an optically active compound which can rotate a plane polarized light to the right. So if you put this rotatory compound inside a cup, a transparent cup, and you allow light, when you have a light from a torchlight, that light will get scattered. Then you can use a nickel prism to polarize it. That is, to polarize it means to make it to move in a straight path. So if it is plane polarized and it passes through that transparent glass to enter inside the optically active compound, then the optically active compound, which is dextro-rotatory, will turn it to the right. While the one that is livo-rotatory will turn a plane polarized light to the left. Now, take note of one thing. Dextro-rotatory compounds are often denoted by prefix letter D or plus, e.g. D-glucose. I told you, I will tell you the meaning of also D-glucose, D-galactose. So if you look at the count of glucose, you write glucose D. That D means that glucose solution can do what? Turn a plane polarized light to the right. Now, livo-rotatory compound. This is a compound that can rotate a plane polarized light to the left. Their name is often denoted by prefix letter L or minus sign. So, e.g., L-glucose. Now, let me show you an example here. Look at lactic acid, CH3, CH3, CH, COOH. If I place a mirror here, this one changes to HOOC, CHOH, now CH3. Now this one becomes H3C. You can see the mirror. Look at the mirror image of this one. This is CH3, but now it's H3C. COOH is now turning to HOOC. So they are not superimposable. What about glucose? 2, 3, 4, 5, 6. So if this is OH, H, OH, and OH, H, OH, and H. This is D-glucose. But by the time I put a mirror in between, the image I'll be shown is going to be like this. 2, 3, 4, 5, 6. Now see, where you have OH is H that will be here. Okay? Now, everything H will be here. This will now turn to OH. What was here before, it is now going to be OH, and H will now come here. Here now it's now going to be H. OH will now go to the back. It will turn around. This will now be H. This will now be OH. So this one is L-glucose. The normal glucose structure we have is the D-glucose. While the mirror image turns everything that is here to the other side, it forms the mirror image. Now, okay? So quickly, let's look at properties, features. Features of optically active compounds. Number 1, they rotate a plane polarized light to the right and become dextrorotatory and be called compounds. Then 2, they rotate a plane polarized light to the left and be called what? And be called LIVO-rotatory compounds. Then number 3, they have at least one special carbon atom called asymmetric carbon or chiral center. In their molecules. So now, inside their molecule, they have one special type of carbon that is called chiral center. They are called chiral center. Now, I will show you that. Now, what is a chiral center? Now, a chiral center is a carbon atom that is covalently combined with 4 different substituent groups. B, C, D. No two of these ones around the carbon is the same. Look at this. This carbon is not chiral because it joined to 3 carbon atoms. You know, another way of writing it is this, CH3. Another one is here. So already 3 of them are the same. So this is not chiral. This one, another way of writing this one is this, OH. It's only joined to 3 group, 1, 2, the remaining thing here. But it must be 4 group for it to be chiral. But this one is joined to COOH, which is different from OOH, different from CH3, different from hydrogen. That is chiral center. Then look at this one. This one has how many chiral centers? So apart from this and this, the remaining 4, 1, 2, 3, 4 are chiral. Let's check. This carbon atom is connected to OH, which is different from hydrogen, different from CHO, and different from everything that is here. This is one chiral center. This is another chiral center. Hydrogen is different from OH, different from what is up and different from what is down. Then this is another chiral center. It's connected to hydroxide, different from everything here, different from hydrogen and different from what is up here. Chiral center. This is another chiral center. OH different from hydrogen, different from CHOH, and different from everything that is here. So that's it. So we have 4 chiral centers. So from here, another thing is that the number of mirror images of an enantiomer can be determined using the formula 2 raised to power n, where n equals to number of chiral centers. So in glucose now, glucose has 16 mirror images as n equals to 4. Then we have 2 raised to power 4. That's 16. 2 times 2 times 2. 2 in 4 places. 2 times 2 times 2 times 2. 2 times 2, 4, 4 times 2, 8, 8 times 2, 16. So that is that. So we are drawing the cuttings here for enantiomers. I hope you understand enantiomers. In the next video, we are going to look at their stereoisomerism. So see you at the top. God bless you. I remain my humble self, Afia Johnson. Do remember to share this video, like it, and subscribe. God bless you, and bye for now. Thank you.